For centuries, architecture and industrial engineering have been bottlenecked by human computing limits. Designing a bridge, an airplane wing, or a skyscraper required months of manual drafting, stress testing in complex CAD software, and tedious regulatory recalculations. But in 2026, we are entering a radical new era known as generative spatial design. We are moving away from standard visual AI tools that simply sketch concept art. Instead, advanced spatial AI systems are directly integrated with physics engines, materials science databases, and localized building codes. This allows humans to materialize complex, factory-ready physical objects and entire structures using nothing but natural voice commands. The numbers behind this industrial paradigm shift are staggering. The global generative design market is projected to rocket from $2.1 billion to over $8.4 billion by 2032, expanding at a compound annual growth rate of 19.3%. This hypergrowth is driven by a massive economic crisis in global construction, rising material costs, and aggressive carbon reduction mandates. Buildings and construction are currently responsible for nearly 37% of global greenhouse gas emissions. Traditional engineering practices routinely overuse steel and concrete by up to 40% just to maintain a safety margin. Generative spatial design eliminates this waste entirely. Imagine a structural engineer standing on a construction site, speaking directly to a specialized AI data agent like Energent.ai. The engineer says, "Design a 50-meter structural roof truss using recycled steel, maximize natural light penetration, optimize for 150 kilogram per square meter snow load, and minimize total material mass." Within less than 30 seconds, the algorithm evaluates thousands of geometric iterations, running structural analysis and checking compliance with international building codes. It outputs a complete 3D schematic ready for computer-aided manufacturing and robotic assembly. The visual output of generative spatial design is redefining the aesthetics of our world. Because the algorithm optimizes purely for stress distribution and weight reduction, the generated structures abandon traditional geometric blocks. Instead, they utilize biomimicry, creating organic forms that look remarkably like the cellular internal structure of bird bones or tree trunks. In real-world engineering benchmarks, these generative biomimetic parts are up to 35% lighter than human-designed components, while maintaining the exact same structural integrity and load-bearing capacity. The timeline for widespread urban adoption is fast-tracking. By 2027, architectural firms expect AI-assisted spatial design to handle over 60% of early-stage urban infrastructure modeling. By 2030, the integration of generative design with advanced metal 3D printing and modular prefabrication will allow custom-engineered residential buildings to be designed, permitted, and physically manufactured in under 7 days. Looking toward 2035, generative spatial design will merge with smart contact lenses and augmented reality, allowing teams to adjust structural elements of a city in real time using vocal prompts directly on the construction site. The line between human imagination and physical infrastructure is permanently dissolving. We are no longer drawing the future, we are speaking it into existence.